Good afternoon and welcome to the DEHN Lightning is Awesome webinar series. We're really excited about today's session. We're looking forward to audience interaction through a series of polling question mechanisms that allow us to get immediate feedback from the audience on our topics as we move through the Lightning is Awesome presentation today. I'd like to point out on our screen is the dial-in number. If anybody's having trouble with their audio, they can also come in through their handset. So thank you. I'd like to get us moving in our interactive webinar session, August 6th, 2020. By way of introduction, I'd like to introduce myself, Mark Hendricks with DEHN Lightning Protection, and my colleague Stephen Weber, who's running the back channel and helping organize the polling questions we'll be seeing. Thank you.
Hello, everybody.
Okay, so today's topic is really about presenting the basics of lightning that have been well established since on or around 1756, when our friend Ben Franklin introduced the air terminal down conductor earthing concept in the Farmer's Almanac and put it into public domain to allow people to prevent fire on their structures. So he patented it, put it in public domain, and since then people have been able to understand and protect buildings from fire. So we've got a photograph of a slightly used rod from that era. So you can see they were using whatever was convenient types of material based on availability. So they may not have had high-grade copper ready to throw on the side of a building, but when it comes to lightning protection, we've certainly improved the state of the art. So DEHN is a leader in the industry. We're heavily involved in standards, and we literally wrote the book on lightning protection. So our session today is intended to demonstrate step leader attachment, how the electric field provokes step leaders, how the final attachment forms, and the actual charge moving through the air into the lightning protection system. The pillars of lightning protection. We'll discuss air terminals, down conductors, earthing, separation, and bonding. And within bonding, we'll talk a lot about the surge protection device topics. So we'd like to start and have a few polling questions to the audience and get a feel for how our interactive session is going to proceed. So I'd like to let Stephen take and start presenting the first question, and you'll see this come up on our screens. So we're interested to understand the audience, and so this is just a quick understanding. Select what you think is the best fit for your expertise and your market segments that you operate in, and we'll let Stephen collect the answers, and when he's got enough of a quorum, we'll go ahead and illustrate what the audience demographics look like. And yes, waiting for a few stragglers.
We've reached our quorum and our results today.
Okay, well, great. We've got a good, strong attendee from some of my friends in the power industry. Excellent, thank you. And some manufacturing, good representation. So thanks for that. Okay, let's move to the next polling question. And just want to understand, are you more focused towards the operation side of your facility side, or are you more of a designer, product design or facility design, or side of your particular work focus? This will help us understand more practical or more design related type approach to questions.
We've reached our quorum and the results.
Okay, so a little bit of a split, but we've got a good field of designers who might be able to benefit from more theoretical design type discussions. Appreciate that. And our third opening polling question is to help us understand, what is your familiarity with lightning problems? How often do you encounter grounding and bonding issues? And that's a couple of times between 2 and 10, or more than 10 times per year, which is, my friends here in Florida know that very well. So we'll give the audience a moment to select what they think is about what their experience is. Excellent.
Quorum's been reached.
Oh, okay. Well, this is highlighting Florida, so welcome to the party. Excellent. Thank you for that feedback, everybody. Want you to get a feel for how the questioning works. We have a series of technical questions that will come and are part of the overall body of how we want to discuss the topic. So lightning, its charge moving through the atmosphere essentially for miles, up to 10 miles. What it tends to do is travel horizontally through something that's like that cold layer, where it's going from liquid to ice particles. The granules, the dropple tends to help accumulate huge amounts of that charge. So it tends to be part of the channel that wants to form. And it's jumping through the atmosphere in step liters. And it can have a certain distance of that step liter. It tends to be, the bigger the charge, the farther it can jump. And that's related to the amount of current, and we'll see some of that. But at the close approach, you see that momentarily that charge is provoking an electric field against all the buildings in the vicinity within its sphere of influence. It radiates spherically, and so it looks like a big ball of electric field. So the charge is very focused, but it's producing this huge field, and it's provoking electrical tendrils from everything according to its electric field strength. So if you're out there on the golf course and you feel that tingle on the back of your head, you're one of those tendrils. And what will inevitably happen is one will attach. Now, what can also happen is you'll see small little attachment points that didn't form the main ionizing channel. And then that main ionizing channel is what's described as the lightning bolt, and you get lots of charge moving one direction from the cloud into the earth, or from the earth into the cloud. They have several, cloud, positive, negative. So there's permutations, but it essentially forms a channel. And everything around it forms these small tendrils that want to also attach. And then you have the main return stroke, which is where all the major lightning parameters are derived from that main stroke. And it's that sort of last moment that we want to talk about a little bit more. This is a really wonderful photograph I first saw from National Geographic, but it's also on the cover of Martin and Raykov's text on the subject, and it's a sycamore tree getting struck by lightning, which tells you don't stand near trees. And we're seeing it just recently here in the Carolinas, where people are being killed by lightning because they're on or around trees during an advent of a lightning storm. Don't be that person. Get away from those types of structures. But it's a really nice photograph because it shows the little lightning bolt talking to that radio tower off to the left. And what's really important about this snapshot, it demonstrates precisely that you're getting lots of provoked smaller step liters that are trying to attach. And there's plenty of damage that can still burn out that TV and the electrical wiring of that house that's next to this structure. So it's a really good photograph that shows us a lot of those parameters we were just talking about, because what comes from that is the understanding of the sort of the spherical electric field, and then how it wants to attach. So where are the likely points that you want to put lightning rods in this scenario, for this structure? So it is that last step liter that we discussed to talk about the rolling sphere, and it's basically a depiction of the electric field provoking responses from everything around it. So we have a polling question. We'd like to get the audiences to help us understand the wisdom of lightning. And this is really the idea here, is that when you have a large enough group of people giving you their impression of the information, you'll get something that looks like the prevailing wisdom. So I'd like to get the audience's response, and obviously it takes a moment to read through, so I don't want to rush everybody. But I'd like your impression of the rolling sphere radius. It represents A, the theoretical attachment point for a step leader. The rolling sphere represents the distance a step leader can jump. The coverage calculation over a structure. So, and I know it sounds a little muddy, I just want your impression of what you think is the most appropriate answer of what the rolling sphere radius represents. And it'll help us drive our discussions. Aha, the polling results are in. The coverage calculation over structure is in fact a correct answer. They're actually all very similar and correct answers of themselves. So, and I know that sounds like a trick question. I just want your impression what you think is the most appropriate. So the rolling sphere radius represents the coverage calculation over structures, but you can see that it's tied together. The theoretical attachment point is where it would have attached, or the distance a step leader can jump is what we call the radius, and you see this in the NFPA and the IEC standards as a radius it can jump, and then you can make your calculations over a structure. So you can see that the answers are tied together. So the pillars of lightning help us understand how to deal with that electrical charge that wants to move through your structure. An unprotected structure is prone to fire. So the application of lightning protection system gives you the benefits of fire protection through an air termination system, a down conductor to get it from the air terminal down to the earth into an earth termination electrode, the grounding rods, a grid, a ring around the structure, or the in many cases the concrete electrode, the foundation electrode. But we need to pay attention, Simon, while we're doing this, three major functions, we also need to pay attention to how we do it, how we space it away from the other critical electrical apparatus, your chillers on the roof, your other electrical systems that run through the walls of the structure. And then the fundamental issue of bonding, lightning equipotential bonding. The point being that two pieces of steel that are on or around the lightning will experience different voltages if they're not bonded together. And if there's different voltages, you now have invited lightning into the actual problem is now in your structure. Those different voltages will now play havoc. And so we have an interactive polling question. We'd like to talk about this. What is the mechanism? How does lightning induce surges? And again, you might see this that we're looking for what you think is the best fit. Is it direct strike onto the power lines, for instance? They're up there high and they're very prone to electrical discharge. Is it the electromagnetic induced current into the wire? Is it mostly the ground potential rise provoking a voltage from line to ground? And then that is what's inducing the surges. What as an audience, I'd like to get your feedback on what is the most similar, the most best fit for what you think is how it's actually happening. What is happening? Electromagnetic induced currents from adjacent type structures. So it's not always just getting struck by lightning. There's more to it. I get that. And that's, again, most of the it's very easy to look at these answers and say, well, in this condition, it's probably direct coupling, or in this condition. So what I'm actually looking forward to is how this might drive some of our questions from the audience back to us as well. So again, these answers help us drive the information in a most appropriate manner for you. So this is really interesting too, because it points out that it's not the direct strike. There's lots of lightning that you can get that isn't directly striking your structure. So that's really great information. Thanks. So lightning charge, it's described mathematically in order for us as an industry to simulate and derive effective measures to protect. So how do we know a lightning rod or a down conductor is going to actually withstand what we say is lightning? And this is a really important portion of the IEC methods, is because all of the equipment in the IEC methods are tested with these parameters. And then that way they're designed and tested, and the user knows that it's for the purpose of lightning protection. And in the UL NFPA methods, they're designed to mechanical robustness, which is also important because you need to be more, you can see in these parameters, there is heating effects, there are jerking effects where the wires want to rip themselves off the wall. And we've seen these at many installations where the down conductors are jerked out of their holders by the lightning events. And so this is an important mechanical aspect of it in the way that UL specifies the materials. So we have the charge, you have the charge in motion, which is current, and then you have the steepness of the current rise, and then we have the overall energy that's transferred through the event. And so those factors give you a reasonable representation of the parameters for lightning, and the peak parameters is what we'll take a look at. So the peak parameters recognized by the IEC methods is up to a 200 Ka peak current. What you see in the NFPA and UL methods is something that looks more like LPL3, which is 100 Ka. In NFPA, it's 100 Ka 8 by 20, and that is used as the strike. And then in NFPA methods, they understand, and it's fairly well represented, that the energy is then divided. So some of it goes direct to Earth, some of it propagates backwards, and you can see that in the methods. But these are the parameters that are used to describe lightning, and from this we get what are described as the peak and the lowest level. Not all lightning is created the same. I mean, there's many species of lightning in who's who in the zoo, and what you see is very large strokes that occur, somewhat rarely, but very large. And then you also get a minimum size stroke that is also very rare, because it takes a certain amount of punch just to be a lightning bolt in the first place. So there's somewhat of a lower limit of 3 Ka that accounts for all of the small baby lightning. And when we look at studies from places like what used Vaisala, what's StrikeNet, they identify the lightning characteristic as a storm moves through, and you can actually see all of the population of lightning in a given storm, and you do see lots of low-level lightning. So it's really important to understand that. But that drives the rolling sphere radius that's used in your risk control. So when you want to control the risk at your hospital full of babies and oxygen, fire hazard, you want a smaller rolling sphere radius to get all the nooks and crannies that could occur from a small population of lightning strikes. If you're less dangerous atmosphere and less population, easy to evacuate structures, but small number of occupants, you can use a lower risk level, and that's you're basically understanding that you can easily control your risk of fire then. So that actually has a larger radius, essentially fewer lightning rods than a high risk application. Like LPL1 has more lightning rods applied, and you can see that you would need fewer if you accept higher risk. Okay, so that gives us an indication. The current is, turns out that the current is the dependent factor, and in the best understanding of how that lightning step leader will propagate is a low current to an exponential factor gives you the radius in meters. So out comes it's a fairly good approximation, but what's important is that it also agrees between the IEC and the NFPA methods, British standards. They have a very similar 45-meter LPL3 class of lightning. And when you apply a 45-meter rolling sphere, you get a reasonable correlation between NFPA and IEC methods. There's other methods, rolling sphere methods. There's also protection angle. So you can have a tower and it will offer protection around it. You can have a mesh spread across your building, and that will allow it to serve as a lightning attachment and down conductor system. So these methods that you apply over your structure, depending on your structure, it may be easier to do one or the other. Complicated structures, it turns out, are actually benefit from the rolling sphere method because it lets you strategically place lightning rods on structures that get the most efficiency for both attachment and for the cost of the system. So what's happening? You're getting lightning into a building and it's flashing into the electrical wiring. So if you don't pay attention to all 5 aspects, you can have any combination of damage. So what's interesting about this photograph is it's showing that, yeah, there was a down conductor system maybe along the outside, but it flashed into the internal electrical wiring. And this, of course, would have caused lots of fire damage. So the air termination system, we really want to see, what that should look like. And so the air termination system is composed of those air terminals placed strategically to avoid connection with your apparatus that otherwise is on the top of your structure. So what's important about these illustrations is the separation between the air terminal to the solar panels, the separation of the air terminal from the antennas and the chillers. You don't want to actually inject the lightning current into that chiller. Depending on your geometry, you want to divert it away from the chiller. You want to protect that stuff. You don't want to actually inject it into your victim. You don't want to do the lightning any favors. It's already going to get there. And so, Stephen, I want to make sure we're not missing any of our important questions. Do we have a question coming up soon?
Yes, right after this slide, we'll have the next.
Okay, just want to make sure. I want to make sure we got this phased right. Yes. So what's important about this photograph and the illustrations is looking at you now have a down conductor system and you want to watch for everything that's around it. So it looks convenient to run a down conductor down that portion of the building. It's out of the way. It's not being touched by the neighbors, and it's not a high traffic area. But what in this case the design has done is its separation distance is so close to that electrical wiring, it's almost certain to flash into that circuit. So you might have radios, temperature sensors, in this case, emergency lighting, outdoor lighting. So you're injecting lightning currents directly into an emergency lighting system that is in fact required to have surge and lightning protection. So you've just introduced it to the most vulnerable emergency system. So the next topic, in our discussion is going to be on the earthing system. And this is a very common question. And I'd like the audience to help us understand how you see it in your standards and specs and how you see it in your field of practice. And it looks like trick questions. Again, it's on purpose. So, and this may spur some side questions that the audience may choose to submit. There's always in case of course, but how far apart what's the best answer to how far apart earth rods should be placed? And should that be the depth of the rod equals the spacing between them? Is it 20 feet? Is it 6 meters? Which is close, but this tell me a little bit about how the audience is thinking, by the way. And or is it less than 20 feet? There may be numbers, you know, in other standards that might describe that spacing. So I'd like the audience to please contribute what you think is the best fit answer. We have a quorum. Depth of the rod. That's very commonly seen, is the depth of the rod is the effective spacing that you shouldn't go closer than the depth of the rod. If you go any closer than the depth of the rod, you're effectively influencing electrons that are trying to go into the soil, and you're losing the efficiency of the rods. It's sometimes that's what you got to do. I get that. I mean, you only have so much free space. It's, you know, property value. You know, there could be electrical service lines, but for best practice, you'll want to space that rod something like the depth apart. And if you get any closer, you're not really being that effective. If you go farther apart, you're missing, you know, you're also not as efficient. So it's a trade-off. The other answers actually are right also. The standards give you 6 meters, 20 feet. And also there you see some standards that indicate 16 feet apart. So this is, you'll also see people say, well, it's the spacing of the fence poles. I'll need another rod every so many fence poles. So that seems to be a reasonable answer. Thank you. So that gets us to the topic of Earth Termination System. What we'd like to present our baseline information is the IEC methods and of course the NFPA methods and National Electric Code. They do recognize two basic fundamental types, where you have what looks like a single earth rod into the soil, and that would be considered something we call the type A, or the type B, which is more like what you think of as a ring, a grid, a ring around the system, or in this case, also the foundation counts as sort of a ring around the facility. But these are very common. There's also permutations, things like a concrete electrode, an encased electrode, things like that. The Ufer ground is very commonly seen. And things that we see that are like fence post grounds, or a grid, which is actually a big grid of wire buried in the soil with electrodes vertically driven into the soil every, you know, so many, for instance, 20 or 16 feet, or where it's appropriate on the site. So, you know, the prevailing things get up half a meter deep below the frost line. Well, we're in Florida, so you got pretty liberal, but you still want to meet the minimum spec then, so it's to drive to half a meter. And the point being is that you don't want to have it near the soil, because it'll actually provoke things like step voltage if it's too shallow. And then you want to be at least, say, a meter away from your building foundation, so that it's similarly it's getting into the soil instead of just directly influencing the building again. And then the ring electrode, where at least 80% of that ring needs to be buried to the appropriate depth. Foundation electrodes are very interesting too, because that it's an effective way to do it, that the encasement can help preserve the wire, the actual integrity of the actual buried copper, and that can be very effective too. And what's really interesting from the IEC methods is the class of lightning protection can help drive your design of the earthing system, so that you can by design intentionally drive the improvements to get a more effective soil earthing electrode attachment. So we talk about in the class 1 system, you'll have a smaller rolling sphere, and that will a smaller radius for the rolling sphere will drive the placement of the air terminals, but also it will drive the design of the earthing system. So in a chart like this, we see if you know that your soil resistivity is, let us say, 500 ohms, then a class 1 system will be suitable. And you'll know that the distance that you have to bury and have immersed in your system is 5 meters of earth electrode. But if you have a class 1 system with high soil resistivity, rocky, sandy, dry, whatever your local version of soil looks like, if you have 1,000 ohm centimeter, you'll actually need a 20 meter ring attachment in order to meet your class of lightning protection system. So it really helps understand how to design and drive that system. So we have another polling question we'd like to get our audience to help us understand what you think is the best practice. So from what type of equipment should down conductor separation be maintained? Buildings, trees, conductive parts, roof-mounted structures are the best fit for this discussion. Interior installations. So, and this might be different for different types of owners. If you're somebody who's running co-located radios at the top of a building in New York City, you have one answer. And if you're somebody who's doing an oil field, you may have a different answer. So I'm interested in this because it helps us drive the discussion points. Polling results, conductive parts, and that's certainly the most appropriate answer for most structures. So again, this really helps us understand what the audience is dealing with, and that's, again, there are some wrong answers. I mean, we're not really too worried about trees, for instance, but or neighboring buildings, but in fact the interior electrical wiring is very important. You don't know what's on the other side of that wall all the time, do we? And so when we're running our down conductor, it can be just inches away from what is in fact an emergency lighting, or the life, an oxygen line, or a hydrogen, maybe it's a gas line, and you're actually inviting a spark to black pipe or something where you don't want to spark over to. So these are really insightful answers about what we're looking for and what the audience is helping us with. So here's some illustrations right out of the standards on what this actually means. Separation from internal wiring systems, from the other parts that are on the roof. So we looked at that. But what's interesting about this is that we have tools available that will let you calculate what that separation distance is on the top of that structure. And this will help guide us in the placement of air terminals so that it's built in to the installation. You don't have to necessarily do extra things if you do your lightning protection layout correctly. You don't have to worry about other equipotential bonding if you can keep it spaced. And so the standards, the IEC and the NFPA methods, are very similar in how they calculate this distance we're calling S. In the NFPA standards, they use D for bonding distance, but it's essentially turns out that those distances are the same for an LPL3 and an NFPA method. So it's nice to see the standards are harmonized. This aspect of a lightning protection system, this is very well globally agreed upon. There is a distance that it will jump into adjacent electrical equipment if this distance is not maintained, this separation distance. And what's also interesting about this illustration is it shows us that even by maintaining the separation distance, you still have to worry about equipotential bonding of all the equipment down at earth level. So here we have a nice illustration with that master distribution bar, the MDB panel, for instance. But at that panel will also be a master ground bar. And at that master ground bar, we'll want to look for surge protection devices, because even though you haven't flashed over, you can still have voltages build up in these electrical systems. And that's what the surge protection device is essentially achieving. So here's a nice photograph of that separation distance. It looked like a convenient way to mount and get the protection angle over this victim. So here we have a probably an air handler box or a control panel for sensing, but what you've got is a metal box on the top of the roof that's right next to the air terminal. So you want the air terminal to be close enough to protect, but you don't want it close enough to side flash. And so here we've done everything right except for keeping that separation of that separation distance. So again, it's very important to really pay attention to how this looks on the top of your structures. So why does a building with an external lightning protection, your air terminals, also require an internal lightning protection system? So we'd like to ask the group your best understanding of the best fit answer. Why does a building with external lightning, which we define as the air terminals and the down conductors, also require internal lightning protection, things like equipotential bonding and surge protection devices? So these are the answers that we think will provoke pretty good thought process, but I'll give the audience a moment. There's a lot to read. I don't want to overly sway your answers, but it's interesting to know that there may be some combination where it's the best fit for your market and for your understanding. Okay, polling results. So most of our audience thought that it was internal lightning protection protects the electric and electronic installations in a building. And that's right, because that's what it's doing. Internal lightning protection is required for lightning equipotential bonding. That's actually also true, because lightning, actually, the surge protection device in the pillars of protection fall under that category. You know, the point being is that if you have two pieces of metal, what was the first thing we said? Is bond them together. Well, okay, you can't actually bond your phase lead of your incoming power. You know, you don't actually want to bond it. That's short. You don't want to do that. You want to produce a control of the voltage, which is what equipotential bonding actually does, is it controls the voltage. Well, that's what your SPD does. And then question C, internal lightning protection prevents surges in the power grid. Well, in a manner of speaking, it prevents things that are inside the building from going back out. Yes, but that's actually more rare. But in effect, you can think of it like a power. If you're a solar power plant, you have internal lightning protection. You have SPDs on the transformers feeding the grid. So that answer may be actually the most important answer if you're in one market or another. So what's good to see is that our answers really help provoke that. So what does the lightning equipotential bonding look like? Okay, so what we're talking about are the metallic bonded structures, all of that building steel, the rebar, the columns, rebar in the columns, the rebar in the each floor of a building is actually part of the lightning equipotential bonding. What we're trying to do with bonding is create zero voltage. You don't want a voltage potential between the column to the floor. You want it bonded. You want low touch step voltage. You want low resistivity through the conductors into the floor, into the earthing system, so that you produce less voltage. You're trying to reduce touch step voltage. You're trying to create 0 volts. 0 volts means zero current between the parts. Bird on a wire. Everybody rises, everybody falls with a lightning event. So if there is some sort of catastrophic nearby wrath of God strike, you actually don't feel it because the voltage from any given surface is reduced. Surge protection devices. Here we go. You guys are all ready. I know you were waiting for this next question. The poll is open. Surge protection provides. So we've got several answers, and again, we'd like to understand what the audience feels is the best fit. Equipotential bonding. Surge protection provides a voltage control. Is it a surge current path? Is it transparent operation with a voltage relief, like a pressure relief? Or my favorite, it's no value if it's not installed. So, you know, some of us may find the answer more appropriate. So, of course, the salesman in my audience will want the answer E. So I was expecting to see that. Thank you very much. I was not disappointed. But also, I see really good some really good understanding of what the surge protection device is doing. Actuality, the A, B, C, and D functions, that's essentially various descriptions, but it's like tomato and tomato. What is there? These were not actually wrong answers. So equipotential bonding, that's the fundamental thing, is what the SPD does, is it tries to create an equipotential bond, but it does it with voltage control, okay? And it does it by diverting surge current so that you've given the surge a safe path that you want it to go. And actually it does provide transparent operation. You don't want your surge protection to actually interfere with your electrical or data communication. It needs to be essentially invisible until you need it. And at that moment, it acts like a pressure relief, like on your water heater. So pressure is in fact the mechanical equivalent of voltage. And so it's like that same analogy of boiling water and pressure valves and things. So we see a lot of terminology come from what used to be the steam engine industry, and we gradually migrated into electronics over the course of the early part of the 19th century. But you see those valves are still in use in my guitar amps today. So it's interesting to see the audience participation. I really like this. Thank you. So that's what the SPD is doing. So pretty much all of the above. And what it's trying to do is create that equipotential bond between that electrical wire and the apparatus. So where does it need to be placed? And that there's a good discussion about zones of protection, where you've got the zone, what's described as the zone 0, where it's actually within the protection offered by the air terminal. But then you can become embedded deeply into a data center or a hospital operating room or a critical control panel at a nuclear power plant. You want to have these built up sort of zones of protection is the terminology. But think of it like layers. You have more and more protected layers around that apparatus to allow ultimately the amount of energy that can disrupt your function to be reduced to its most safest possible level based on your risk. If you're a hospital operating room, your margin for surges is really, really small. If you're out at a pump station and it's just a couple of windings on a motor, you're not too worried about it. It doesn't serve anything, too critical of a function. Maybe that motor is expendable. That's okay. Then your level of risk is lower. So I've got another polling question, and I've got the question started. You might have saw a glimpse, so that was a teaser for you folks. I got more to talk about here. This is a really common question, and I'd actually like to get the experts of the audience to help us understand what they understand and what they employ in their facilities. What's the best way to terminate your shield? Which end of the twisted pair should be bonded? So both, that's appropriate sometimes. That may be the answer. Field instrument end, the more remote end, or the more cabinet end, the controller end, where your PLC, that's often the digital control cabinets end. So is it at the instrument or at the cabinet? So polling results say the cabinet end is more commonly seen in the industry. And I appreciate that feedback from the audience. Although some people, there's a good percentage of the audience says both ends should be shielded. And then we've got some people that do the field instrument side. So this is really good indication of what the mix might look like in our audience. So I've got a nice diagram, and it's got a couple of features that I didn't talk about, but this is what best practice might look like. And this is an interesting application where we're allowing the shield to come all the way through the other end. Let's call it the other end. And here it really doesn't matter which end, but we'll say the other end, just for sake. But what's important about this is that you see that these structures could have substantially different earth electrodes. There could be a distance and a voltage across from these electrodes into the earth. The master bar at number 1 isn't necessarily the same master bar at number 2. And what's important here is that the shield should be maintained to reduce electromagnetic noise, but here we're allowing it to be bonded through a gas tube, indirect bonding. It's bonded when it sparks, momentarily when that sparks. And that's like that relief valve. So in an application like this, what could work well is to have a surge protection device, it's particularly a spark gap, a gas discharge tube on that shield to act like a pressure valve. So any other time during the day, it's open and it's not interfering with current. What you don't want is a bond here, because look, these are different ground. You'll create a real havoc if you have these bonded all the time. So what most is often seen is that you peel back the shield, but it's also possible to consider an additional surge protection gas tube from shield to earth. So in this diagram, we also see the application of a surge protection device on each end, which is also best practice. The remote instrument needs to be protected because you have some valuable process, and the control cabinet end, what we call number 1 in this diagram, needs to be bonded and protected because you have, of course, that critical PLC device or that digital control system on this cabinet 1 end. And then lightning, your enemy that's trying to induce surge, either directly, indirectly, ground potential rise, anything it can, every way it can, it's trying to give you damage. It's like I like to say, the earth is not a friendly place. Everything around you is trying to kill you some way or another. So this is a nice introduction to the topic of isolated systems. If you can't bond it, if you don't want to bond it, you can isolate from it. There are methods. You can use separation distance. You can use products that offer isolation. And this is a nice illustration showing an air terminal mounted on a structure with isolation from the structure and the victim. So in this case, the critical victim is a radio or a radar that has to be, if I'm flying in the airplane, I want that radar protected, right? So that radar is protected under the fall potential. The fall angle. Fall potential. The angle of protection under that air terminal, and then the down conductor leads it to the ground. But we're using isolated materials to put the earth rod far enough away from the actual earth rod of the structure to prevent that ground potential rise. So we're trying to prevent direct side flash. We're trying to prevent GPR. We're trying all those mechanisms that we thought we were worried about, we want to protect from. So we're reducing all of the mechanisms that want to induce surge currents and voltage transients. So this is another polling question for us, and we're moving right along. So isolated lightning protection, it prevents what? It prevents side flash from down conductors. Does it prevent ground potential rise? Does it prevent ignition sources caused by sparks between unbonded metals? So what is your best description of what isolated lightning protection is preventing? The poll is open. The organizer is getting ready to give us the results. Kind of a split between A and C. And again, it's likely that all three are actually the right answer, and it depends on what you're most worried about, actually. If you're on the top of a co-located structure and you're running a police band radio, you're running a police first responder radio, you're actually most worried about probably the things at the top. If you're running a data center in the basement, you're probably really worried about ground potential rise. And if you're worried about ignition sources between unbonded metal, if you're in a tank farm, I bet you're really worried about ignition sources from any unbonded metal. So it depends on your market, and I totally appreciate that. Thank you, audience, for your feedback on this. So there's really no wrong answer, but you know, there's plenty of reasons to apply isolated lightning systems, and they can look as complicated as things like this at a launch complex, where our friends from SpaceX have recently retrieved. They had a splashdown, but the launch occurred from this launch complex in Cape Canaveral. They splashed down out in the ocean nearby, and what we see here in this Google Earth type image is an isolated lightning protection system. And the people that are launching rockets with hydrazine and liquid oxygen are very worried about all sources of lightning damage. So they're reducing everything. I can assure you at this site, they've got SPDs, they've got filters, they certainly have these tall structures around it, which provide isolated air terminal, down conductor, and earthing systems that don't pollute the ground of the actual space vehicle. So in this case, lightning air termination systems, isolated air termination systems, are providing everything they can possibly get, every benefit possible. So here's just a quick glimpse at the standards that are appropriate for a lot of the discussion points. This is just a snapshot. At any given time, there's some really good, appropriate information for your markets and industries. And just a quick glimpse of what we covered today. It was really a good discussion about the pillars of lightning protection, and really appreciated the customer feedback and the questions. And just a quick note for the audience that our material is eligible for continuing education credits based on our license number, and this can all be part of your certificate and application. Please visit us on social media and visit our website for more information. We've got questions that might be open. The session ran a little longer than what we've seen in the past, Stephen. I appreciate the polling. The polling questions really helped bring a lot of insight to us. Are there questions from the audience that we can still address today?
Yes, thank you, Mark, and thank you, audience, for your attentiveness and help with the polls. I've selected 3 very nice questions that I think we will have time for during this session. The first question, Marcus, is the separation distance not affected by the magnitude of the lightning current or the charge in the LPS? He's asking what value is used in that formula that was shown.
Stephen, you in fact are a separation distance calculation expert.
Yes, I just want to say that that formula that Mark showed is what we call the short version, or the simple approach for calculating the separation distance. And you'll notice that in that formula there's a factor Kc, and Kc is selected based on the amount of down conductors that the lightning protection system has. So in other words, if a lightning protection system has only one down conductor, say a single rod or a mast or something, that's the value that Kc then represents. And if it's got 2 or more or 3 more, down conductors, then that's the value that KC would represent. But then in the standard, there's also an advanced or a more detailed approach where you can look at your lightning protection system and calculate what is define a point of strike as being where the lightning terminal is, and then calculate how the current share would be in between all the different conductors and down conductors that you have, and then from there you can then determine from a proportional approach what would be that separation distance. The second question we have here, Mark, is can a surge protection device also improve power or signal quality?
Well, it certainly improves the quality of the operation. So there's a lot of discussions about power quality, and so you have filters, you have surge protection is certainly part of that. Isolation transformers. The other issue with power quality is the sort of the long-term fatigue of an electrical system. Like a piece of wire seems pretty permanent. Like you can put electrical current through it any number of infinite times and you haven't really changed the copper until it's overstressed, and then the dielectric is stressed. So in a typical distribution system that maybe has a 600 volt wire to the UL 1081, that's great, 600 volts. That's probably what the entire system will withstand, the breakers, but 600 volts is not what lightning is. So when you get lightning events, it's overstressing the entire electrical system. So in a power quality discussion, yes, it improves the AC power or even the data signal. It can give you some nice filtering, but it's also protecting the electrical apparatus itself. So it's a big discussion about arc flash and degradation of electrical systems. And again, it's one lightning strike is not going to necessarily degrade your entire electrical system, but if it blows out your main circuit panel, yeah, you pretty much have to replace everything. Great question, yes. Though, about the fundamentals.
Yes, and then the last question we have time for would be, does your principle of shield wire grounding also apply to metal cable trays and the effect thereof on cable conductors, shielded or not shielded?
Yeah, it actually would apply to cabling, grounding, and such. Again, look at the illustration showed two separate ground termination electrode systems. So in a building design where you're going to shield your cable trays, you would choose to leave the one end float. If you know it's going across to across an alleyway and your cables are feeding a structure with a substantially different earth, you really need to be careful about that ground loop, and the cable tray becomes a big ground loop. So yeah, you can inadvertently introduce substantial ground currents into that tray. You're trying to create a clean and a safe and an arc fault friendly environment, but if we're not watching that earthing, that can give you some trouble. And again, there's methods like using a spark gap on that one end that could guarantee that you're not bonded unless there's a voltage. So yeah, the discussion it opens up to larger levels. Okay.
Yes, well, and if you need us to help you with anything in your facility, you know who to contact. Check out our website for upcoming webinars. Thank you so much, Mark. Thank you, audience.
Thank you, Stephen, for the back end, and thank you, attendees, for your participation and help with this webinar. Thank you. I hope it was enjoyable for everybody.